In this lecture, we will go a bit deeper into probabilistic parsing, and we'll finish the course on natural language processing with some summarizing observations and an overview of what has been done during this course of 40 lectures. So, as we said, probabilistic parsing is needed so that we can have a principled scoring mechanism for multiple parse trees in case of an ambiguous sentence. If a sentence is not ambiguous and has a single parse tree, then of course, the score is 1.0. If there are multiple parse trees, then depending on the frequency of the constituents of that parse tree, there is a weightage mechanism which reveals how probable the parse tree is given the sentence, and as evidenced in the corpora. So, we will begin this discussion on probabilistic parsing and go to the slide, but before that we will take up a very important dynamic programming based deterministic algorithm, the CYK algorithm, which is also used extensively in probabilistic parsing by making use of the beta or inside probabilities. So, all this is coming little later. Now, when we look at the parsing problem, we see that lot of work on the way towards building the complete parse tree can be reused. So, for example, if we have this phrase a flight, here this is a noun phrase, a is a article and flight is a noun and a nominal, finally giving rise to a noun phrase. A flight from Indianapolis is a preposition phrase and the flight is a noun, and the whole thing, a flight from Indianapolis, makes it noun phrase. But the point is that this flight going to nominal again, and then combining with a determiner and producing a noun phrase is showing that the previous work on NP can be reused. Now, we have a bigger structure, a bigger phrase, a flight from Indianapolis to Houston. So, in this case too, we find that this whole work on a flight from Indianapolis can be done for building the parse tree for this bigger phrase, a flight from Indianapolis to Houston. And finally, this large phrase tree for the longer phrase, a flight from Indianapolis to Houston on TWA, these can make use of the work already done for a flight from Indianapolis to Houston, which in turn can make use of the work done for a flight from Indianapolis, which in turn makes use of the work done for a flight. So, this kind of shared sub problems is a very common theme in building of parse trees. One can make use of the work done for sub parse trees and can embed sub parse trees for constructing a bigger parse tree. This is quite common, and in computer science we have a mechanism to handle this situation. We can make use of the work done for smaller problems and can create the solution for a larger problem, and the platform which is eminently suitable for this is the dynamic programming platform. We use DP, dynamic programming, in parsing true, and we have a very famous well known algorithm for this called CYK algorithm. So, CYK parsing requires that the grammar is consisting of epsilon free binary rules, and all the rules should be in Chomsky normal form. That is, A goes to BC, that means two non terminals on the right hand side, or A goes to small a, which is a terminal. Now, what if the CFG is not in CNF? Then of course, we can do some pre-processing and we can convert it into CNF form. The CYK algorithm is a very small recursive algorithm, dynamic programming based, The algorithm is best described by means of an illustration. So, this algorithm is Koch-Younger-Kashimi algo, and very interestingly this algorithm is not the joint work of these three researchers. It is not as if they together produced a paper describing the algorithm. What is interesting is that they independently worked with other collaborators possibly to produce this algorithm independent of each other's findings. Since they were almost discovered simultaneously, the NLP field, the parsing field has taken the practice of, has adopted the practice of calling this algorithm CYK algorithm after the name of these independent researchers, Koch-Younger-Kashimi algorithm. We work with our already familiar example, S goes to noun phrase, verb phrase, noun phrase goes to determiner noun, noun phrase goes to plural noun, noun phrase goes to NP and PP, PP goes to PNP, VP goes to verb phrase and preposition phrase, verb phrase goes to past tense verb and noun phrase with different probabilities. And take care of the fact that all the rules which have the same non-terminal on the left hand side have their probabilities summing up to 1, and we have said that the probability value indicates what percentage of time this particular rule is applied in the corpus to produce the sentences. On the right hand side are the lexical probabilities, the probabilities of obtaining the vocabulary words. Now, we discuss the algorithm. For this sentence we have seen before, the gunman sprayed the building with 6 bullets. We saw that this particular sentence has 2 parse trees. In one case, with bullets is the preposition phrase attaching to spray, another case the preposition phrase attaches to building, as if the building has bullets in it, and in this case bullets are the instruments by which the spraying is done, or rather the bullets are the objects which are sprayed. Now, the algorithm proceeds with finding non-terminals for between word positions. For example, the word the gives rise to the non-terminal dt between 0 and 1. So, on the column we produce the indices starting from the first word to the last word 1, 2, 3, 4 up to 7, and on the rows we have the preceding positions 0, 1, 2, 3 up to 6. So, dt, a determinant is found between 0 and 1. So, this from and to means from 0 to 1 we have a determiner. Next stage, we have found another non-terminal noun between 1 and 2. Next stage, we can combine these dt and nn to produce the noun phrase. Between the positions 1 and 2, we have a noun, but between 0 and 2, that is spanning this whole range 0 to 2, we have a noun phrase, which is indeed true. The gunman is determiner noun combination, and therefore, this is a noun phrase as per the rule, grammatical rule. Next, between 2 and 3, we have been able to find a verb in past tense form VBD. Proceeding further, we see that we cannot produce any bigger phrase at this location, which is 2 and 3, which is 1 and 3. So, between 1 and 3, I cannot produce any bigger phrase, because noun and past tense together do not form any phrase. Between 0 and 3, the gunman sprayed, again no phrasing is possible. Now, between 3 and 4, we have found a determiner. Okay, this is the. We do not find any phrase which ends in the. Okay, that is impossible. So, that is why all these columns are kept vacant. There is no phrase which ends in position 4. Then we find a noun between 4 and 5, which is the building, and now we can see that we can keep on finding phrases. So, between 3 and 5, there is a noun phrase. The building is indeed a noun phrase produced from the combination of dt and nn. Then between 2 and 5, from 2 and 5, we can find a verb phrase. Why? Sprayed the building. This is a verb phrase where the verb phrase comes from VBD and P. This, there is a grammatical rule, VBD and P together can produce a VP. So, is the contiguity satisfied? Yes, because you see between 2 and 3, we have a VBD, a verb, and between 3 and 5 we have a noun phrase. So, VBD and NP together can produce a VP which is between 2 and 5. Next we have the P, a preposition between 5 and 6, and now no phrase can end in the preposition with. So, that is why we find that from 5 to 6 there is on the column from 4 to 6, okay, on this column there is no phrase. There is no phrase on top of P because nothing can end in a preposition. Next we see that an NNS is found with bullets between 6 and 7. So, this produce a preposition phrase with P and NP, and NNS is nothing but NP. So, there is a little bit of violation of Chomsky normal form here, or rather we have converted the rules into Chomsky normal form. NP was going to NNS, we have replaced NNS by NP and thereby converted all the rules into Chomsky normal form. So, between 5 and 7 we have the preposition phrase, then between 3 and 7 we have a noun phrase which is the building with bullets. Okay. Then between 2 and 7 we have a verb phrase which is consisting of a verb in past tense and a noun phrase. Then there is nothing between 1 and 7 because we do not have any phrase which begins with a noun. Noun phrase does not begin with a noun in singular form, and finally, we have the symbol S between 0 and 7. The whole thing is then resolved to S. So, this is how the CYK algorithm works. This is a very elegant algorithm and relies on the fact that the grammatical rules are in Chomsky normal form. On the right hand side we have exactly two non-terminals or a single terminal. The single terminal takes care of filling out the cells with non-terminals attached to only a single terminal, and columns and rows can be combined keeping the contiguity information to produce phrases. This is how CYK works. The parse tree can be obtained by keeping the back pointers. So, for example, NNS is between 6 and 7. So, bullets is resolved to NNS, which again is an NP. This is a non Chomsky normal form construct, but it is there for the purpose of understanding. Between 6 and 7 we have a noun phrase, then between 5 and 6 there was a P, between 5 and 6 there was a preposition. So, these two can be combined, 5, 6 and 6, 7 can be combined to produce a preposition phrase between 5 and 7. And then similarly, building and determiner is combined to produce the noun phrase and preposition phrase combined to produce another noun phrase between 3 and 7. So, this is the way the parse tree is obtained by keeping a back pointer, which makes use of the table which is just now completed. Now, this same CYK algorithm is now used to obtain the parse tree of a sentence in the probabilistic framework also. We will see how, but before that let us go back to probabilistic parsing with its definitions and terminology. So, we have already said that the best possible T is the one which maximizes the probability of the parse tree given the sentence, and this argmax is over all possible T's. When we use the Bayes theorem, we get PT into PS given T, and PS given T is 1 because given the tree parse tree the sentence is completely determined, this probability is 1.0, and finally, we have the prior probability PT coming here. So, now the probabilistic context free grammar as discussed in the last lecture consists of a set of terminals, non-terminals, a start symbol which is spatial status symbol, a set of rules. The only new thing is the rules have probability values associated with them. The rule probabilities are such that the probability of the sum of the probabilities of all those rules which have the same left hand side should be equal to 1. Now, this is the grammar, and then this grammar produces for the sentence the gunmen sprayed the building with bullets, two trees. In one tree the preposition phrase is attached to the verb. So, bullets were used to spray the building, and in the other case there is this unlikely parse for with bullets being attached to building, which means it is a building which contains bullets. This interpretation is unlikely, but it is possible to have this kind of attachment. An example of that would be the gunman sprayed the building with women in it. So, that would mean the building has women in it, and with women in it is attached to building. It's that building which has women in it. Now, between these two parses, since the first parse is semantically more plausible, we find that its probability value is higher than the other parse tree, which is less plausible, and the probability value here is 0.0015, the less probable parse tree, and the more plausible parse tree has probability value 0.0225, which is more. Now, how is this probability calculated is our next concern. We have to understand this through the discussion of the meaning of the probability of a sentence. The notation is shown here. WAB is a subsequence WA, WA plus 1, WA plus 2 up to WB. Now, this picture shows that NJ is the root for the sub-parse tree for the sequence of words from WA to WB. Now, since NJ generates WA to WB, we say NJ dominates WA to WB. So, in computer science parlance, we would say NJ generates WA to WB, and in linguistic parlance, we would say NJ dominates WA to WB. Or in the parsing parlance, the yield of Ni should be Ni is the sequence WA to WB. For example, the sweet teddy bear is the yield of the noun phrase NP, or we say NP generates the sweet teddy bear, or NP dominates the sweet teddy bear. The probability of a sentence, how do we compute this? Probability of a sentence with words going from W1 to Wm is nothing but probability of W1 to Wm comma t. This marginalization over all possible parse trees of W1 to Wm, the sequence W1 to Wm. Now, this joint probability is broken up, which is Pt into Pw1 to Mt, and this is nothing but some sigma Pt. So, the probability of the sentence is nothing but the probability of all those parse trees whose yield is the sentence itself. Now, Pw1 to m given t is nothing but the probability of this sentence given the parse tree. This is equal to 1. Okay. So, now the probability of context free grammar model has 3 assumptions, fundamental assumptions. Place invariance, probability of noun phrase going to DTNN is same in locations 1 and 2. So, wherever this rule appears, NP going to DTNN, the probability is the same, it does not depend on the place. Context freeness says that probability of NP going to DTNN given anything outside the child is probability NP goes to DTNN. Okay. So, this means that the probability of this rule is independent of anything that happens outside this subtree NP going to DTNN. Ancestor freeness is that probability of NP DT going to NN, its ancestor is VP, the conditioning part does not matter. So, whatever be the ancestor of NP, NP goes to DTNN has the same probability. So, these are 3 assumptions of PCFG which are used for calculating the probability of a sentence, calculating the probability of a tree, and so on and so forth. So, probability of a parse tree, for this we first understand the notion of domination. We say that Nj dominates from K to L, symbolized as Njkl, if Wkl is derived from Nj, or Wkl is the yield of Nj. So, probability of a tree given the sentence is probability of the tree given that S dominates 1 to L. The start symbol S dominates the word sequence 1 to L. So, PTS is approximately equal to the joint probability of constituent non-terminals dominating the sentence fragments. So, let us understand this by taking an example. Here we have the word sequence W1 to WL, W1, W2, W3, W4 to W5 to WL. So, we have a noun phrase between 5 to L, this is indicated here. We have a preposition phrase from 4 to L, where between 4 and 4, 4 and 4 okay, is a slightly different notation. There is a preposition phrase. Then a verb and preposition phrase obtains verb phrase, and then noun phrase and verb phrase obtains a sentence S. So, DT N combination gives rise to NP. Now, the probability of the tree given the sentence is probability of T given that sentence dominates S dominates 1 to L. So, here this probability of the T given S 1 to L is nothing but the joint probability of the dominations by various non-terminals. So, probability of the parse tree T given S 1 to L is the joint probability of a noun phrase which dominates the positions 1 to 2, a determiner at position 1, then the word W1, then a noun dominating the position 2, then a word W2, then a verb phrase dominating a sequence from 3 to L, a verb at 3 3, a word W3 and so on. So, all these are the domination situations where the word dominates itself, the non-terminals dominate sequences. Now, what we do is that we take this joint probability and apply conditioning on this and then make independence assumptions. So, for example, okay, NP and VP are isolated given S. Now, we isolate DT and N given the NP. We also have to bring in the VP and S, but because of the context freeness assumption, this VP has no influence on the probability of this NP going to DT and N. So, I can drop the VP and S here. Similarly, probability of W1 given DT is independent of NP here because of ancestor freeness assumption, and these VP here again because of context freeness assumption. So, anything that happens outside this subtree is immaterial, even the ancestor's influence is not felt. So, that is why we have probability of W1 given DT. So, we use chain rule, context freeness and ancestor freeness, and thereby obtain the fact that the probability of the tree given the start symbol S okay, is nothing but the product of all possible rule applications, product of the probabilities of the rule applications. So, this is the main theory behind calculation of the probability of a parse tree. We just detect or note the probability of various dominations, that means the probability of various subtrees which obtain in the tree, and then take the product of the probabilities. But why product? Product because of the fact that first we convert the tree into the probability of the tree given S to joint probability of all the subtrees. Is that okay? That is okay because you see the domination by S is nothing but the joint domination of non-terminals in the subtree. So, this we have to accept because the domination of S is nothing but the result of domination of individual non-terminals on different parts of the sentence, that is that. Okay. And after that, after we have obtained the joint probability, we apply chain rule, and when we apply chain rule, we isolate those subtrees and the root of that subtree which are dictated okay, or which are entailed by the grammatical rules, and then we apply chain rule, and when we apply the chain rule, all those variables which are outside the subtree or in the ancestor are dropped because of ancestor freeness assumption and context freeness assumption, and invariance of course holds, because wherever a particular subtree with same left hand side and right hand side obtains, the probability value is same. So, this is a very instructive slide which shows what is it? What is the theory behind the calculation of the probability of a parse tree? Okay. So, we proceed further, and if we use this theory, then we can compute the probability of this parse tree. We can see why it is coming out to be 0.0015. S goes to NPVP as probability 1.0. So, this is 1.0. NP goes to DTNN, probability 0.5. So, this is taken here. DT goes to the probability 1.0, fine. NN goes to gunman, probability 0.5. VP goes to VBD NP, 0.4 is the probability, here is 0.4. VBD goes to sprayed 1.0, here it is. NP goes to NPPP with probability 0.2, here it is. NP goes to DTNN, probability 0.5, here. PP goes to PNP with probability 1.0, yes, 1.0. P goes to with, that is 1.0 here. Then NP goes to NNS with probability 0.3 here. NNS goes to bullets with probability 1.0 here, and when we multiply these values, we get 0.0015. Now, we have remarked before that hidden Markov model and PCFGs have lot of correspondence. Hidden Markov model is on the linear sequence of words, probabilistic context free grammar is on the tree. So, we apply the same theory, very similar theory for tree as opposed to a sequence. Now, in HMM, we have three important algorithms and situations. So, we see here in HMM we have the observed sequence, the corresponding thing in PCFG is the sentence. X is the state sequence in HMM, T the parse tree is the corresponding entity in PCFG. Mu is the model for the HMM, G the grammar is the corresponding entity for PCFG. Three fundamental questions are addressed in HMM. How likely is a certain observation given the model? How likely is a sentence given the grammar is the corresponding question. So, P O given the model is equal to P sentence given the grammar. How to choose a state sequence which best explains the observation? This corresponds to the question of how to choose a parse tree which best supports the sentence. The corresponding expressions are shown here in hidden Markov model. What is the probability of the state sequence X given the observation sequence O? Similarly, argmax over all possible parse trees given the word sequence. Here we have argmax over all possible state sequences given the observation sequence O. How to choose the model parameters that best explain the observed data? This is the question in HMM. How to choose rule probabilities which maximize the probabilities of the observed sentences? This is the PCFG question. So, now we take up this question of how we construct the probabilistic parse tree. The following interesting probabilities. If we look at the slide here, we take this sentence, the gunman sprayed the building with bullets. So, the building is the noun phrase, sprayed the building is the verb phrase, the gunman sprayed the building with bullets is generated by the start symbol N1. So, what is the probability of having a noun phrase at this position such that it will derive the building? This is known as the inside probability, denoted by the notation beta. So, what is the probability of finding a noun phrase between the positions 4 and 5? This is beta. And what is the probability of starting from N1 and deriving the gunman sprayed a noun phrase and with bullets? So, this is known as the outside probability. The bullets is having its own parse subtree rooted at NP. So, the alpha probability gives us the probability of this whole subsequence, the gunman sprayed, then a non-terminal NP appearing, and then a sequence with bullets coming after that. The interesting probabilities are as follows. The random variables to be considered are the non-terminal being expanded, the word span covered by the non-terminal, and while calculating probabilities, we consider the rule to be used for expansion. Outside probability is better illustrated in this slide. The probability of beginning with N1 generating the non-terminal NJPQ and all words outside W P2 Q. So, alpha JPQ is denoted this way. The joint probability of the word from 1 to P minus 1, then NJ dominating the subsequence P to Q and the sequence WQ plus 1 to M. Beta JPQ is the probability of generating the words WP to WQ starting with the non-terminal Nj Pq. So, beta j Pq is nothing but probability of W Pq given that Nj dominates the subsequence Wp to Wq. Now, calculating the inside probabilities is again a dynamic programming based recursive algorithm. So, we have already seen the CYK algorithm for the deterministic situation. The grammar is in Chomsky normal form, and each non-terminal gives rise to two non-terminals side by side, or it produces a terminal only. Now, in the dynamic programming based algorithm, a table is maintained, a matrix is maintained starting from position number 0 to the last position, and in the column we have position starting from 1 to last plus 1 position. Okay. And then between any two positions we try to find a non-terminal given the word, and then we try to combine these non-terminals to form bigger phrases. So, beta j kk is the base case. The notation is slightly different here now. This is nothing but the probability of the word k given that Nj dominates this kth position. So, probability of Nj kk going to Wk. The base case is used for rules which derive the words or terminals directly. So, suppose Nj equal to Nn is being considered, and Nn goes to building is one of the rules with probability 0.5. Then beta Nn for 5.5 is probability of building with Nn, a noun dominating position 5. So, probability of Nn going to building given G, the probability is 0.5. The induction step is the most interesting step. We assume grammar in Chomsky normal form, and beta j p q is probability of the word sequence p to q given Nj dominates it. Now, this is nothing but a marginalization case. We vary the position d, okay, and which will also vary the non-terminals which dominate the sequence from d to q and from p to d, from d plus 1 to q and from p to d. So, we have two non-terminals nr and ns. Now, when rns varies and d varies from p to q minus 1, then we get this expression here by applying various kinds of independence assumptions, ancestor freeness, context freeness, and joint probability. So, this you can say is nothing but the domination of nr and ns. So, this whole expression can be written as probability of w nr ns given nj. Now, nr ns can be isolated. After that, when we have nr going from p to d and then ns going from d plus 1 to q, we have these two beta probabilities, beta r p to d and beta s d plus 1 to q, and probability of nj going to nr ns. So, this is simply the probability of the rule, and the beta values for p to d and d plus 1 to q have to be recursively found out. Now, we can understand the inside probability algorithm by taking this simple example of a small phrase, the huge building. So, we split here for d equal to 2, then d equal to 3 and so on, and we consider different non-terminals which can be used in the rule, and the algorithm is a bottom up approach. The idea of induction is consider the gunman, we apply the unary rules, dt goes to the, nn goes to gunman, probability is 1.0, probability 0.5. So, dt goes to the 1.0, nn goes to 0.5, np goes to dt nn with the probability 0.5. So, the induction is that the probability that a noun phrase covers these two words p np goes to dt nn and p dt deriving the word the, p nn deriving the word gunman is equal to 0.5 into 1.0 into 0.5 is equal to 0.25. Now, just like CYK algorithm, a parse tree, a parse triangle is a data structure which helps this operation very well. The parse triangle is constructed for calculating beta j p q. The probability of the sentence can be found out again from the beta probabilities. So, probability of w 1 to m given g is nothing but probability of n 1 dominating w 1 to m, and this is nothing but beta 1 1 to m. that means n1 dominating the sequence of words from 1 to m. So, just like CYK algorithm, we first fill the diagonals with beta j k k values. Here is the first location between 0 and 1. So, there is a there. So, there we find beta dt is equal to 1.0, because the probability of dt going to the is equal to 1.0. Then at gunman we find a noun. So, the probability of that is 0.5. We record this beta nn between 1 and 2. Okay. Then beta VBD is sprayed, probability of the verb going to sprayed is 1, beta dt is 1.0, beta nn is 0.5 like before, beta p is 1.0, preposition goes to with probability 1.0, beta nns equal to 1.0. Okay. That is because nns going to a plural word, the probability is 1.0. So, first these diagonals are filled. Now, we try to see how we could obtain the probabilities of the phrases. So, we see here nn and dt can combine to produce the noun phrase, and we see how beta np 1 to 2 is obtained. Probability of the gunman dominated, given that there is an np between 1 and 2. So, this is probability of np going to dt nn, which is 0.5, and then probability of dt going to the, which is 1.0, and probability of nn going to gunman, which is 0.5. So, the probability comes out to be 0.25. So, this is the way the parse tree is produced. Let us see a few more entries. Let us see beta VP between 3 and 7. There is a VP. Now, here there is an ambiguity consideration. Sprayed the building with bullets should be attached to spray or building. So, since it is a probabilistic framework, we have to sum up the probabilities of both the parse trees, and these can be obtained by beta VP 3.7, 3 to 7. So, probability of sprayed the building with bullets, given that there is a verb phrase between 3 and 7, 3 and 7. Okay, here there should be a verb phrase. And how do you obtain this? This probability of verb phrase going to VP PP, this is preposition phrase attachment to verb, into beta VP 3 to 5, beta PP 6 to 7, plus probability of VP going to VBD NP, this is noun attachment of the preposition, beta VBD 3.3 and beta NP 3 to 3 and beta NP 4 to 7. So, 0.61 0.3 plus 0.41 0.015, the beta value for VP here, okay, 3 to 7 comes out to be 0.186. So, this is the way one goes on filling the entries in the cell, and finally, the probability of the tree comes out from the beta value at this location, which is the location for S. So, this is nothing but CYK algorithm, as you can see. This is nothing but a CYK algorithm, which is dynamic programming based. Only thing is that the probability values are used and they are combined together, obeying the theory, okay, which is used for computing the probability of the whole tree. So, given a sentence, what is the probability of this sentence? There is nothing but sum of the probability values of all the trees which can come for this sentence. So, between 3 and 7 we can have 2 parse trees, that is why 2 probability values expressions are taken and summed up. So, now there is a Viterbi-like algorithm for probabilistic context free grammars. It makes use of this delta probability, and this is the highest inside probability parse of NI PQ. This is very similar to the Viterbi algorithm for the best state sequence for an observation sequence, linear observation sequence, and the same dynamic programming like approach is used for finding the best possible parse tree. So, we see here again in the with respect to the example, probability of sprayed the building with bullets, given that there is a verb phrase between 3 and 7, is maximum of the 2 probability values. What 2 probability values? One is PP attachment to verb, the other is PP attachment to the noun. So, here the probability comes out to be 0.18, the probability value comes out to be 0.06, So, we will adopt this subtree as the tree for the verb phrase, and this is obtained by keeping track of delta, which is the maximum of all the parse trees. So, Viterbi-like algorithm with backtracking and so on, this is an efficient algorithm to find out the probability of the parse tree. Grammar induction also can be done on the parse trees, and we use the annotated corpora like the pen tree bank, and the algorithm proceeds in terms of an expectation maximization, iteration between expectation and maximization. So, in the expectation phase, we start with initial estimates of the rule probabilities. We compute the probability of each parse of a sentence according to the current estimates of the probability. We compute the expectation of how often a rule is used, summing the probabilities of rules used in previous step. We refine the rule probability so that the training corpus likelihood increases. This is the maximization step. So, this continuous oscillation between expectation and maximization gradually leads to the stabilization of the probability values for the rules. Outside probability is also used, and probability of a sentence can again be computed by means of outside probabilities. So, this then finishes the discussion on the probabilistic parses, and what we have done so far is that we gave a theory of how to use probability in probabilistic parsing. Now, the calculation of these probability values for the rules obtained from the training corpora. So, the training corpora can be either marked with bracketed structure, which leads to the situation of supervised learning, or the training corpora could be without any bracket marking. So, this is a case of unsupervised learning. When we get the rule probabilities from bracketed training corpus, then we can make use of a frequency based approach, a simple frequency based approach. We simply calculate how many times a rule has been used, compared to other situations where the same non-terminal of the rule is used, but not the same right hand side. So, from this calculation we obtain the probabilities of the rules. So, this part I could write probability of a rule, which is nothing but probability of A goes to B C is nothing but number of times A goes to B C holds divided by number of times A holds. Okay. So, this is nothing but number of times sigma A goes to zeta I over all possible i's. Okay. So, this is nothing but a frequentist approach to probability calculation. The probabilities of the rules are found this way. However, if this calculation is not possible, because we do not know how many times this rule is applied, we can obtain the probabilities by the EM algorithm, EM based algorithm, which is the inside outside probability. Now, it is time to summarize the course. I will just go over them. When we started the course, we first discussed a number of ambiguity examples, which obtains in case of natural language processing. Natural language processing is divided into number of stages which are classically accepted: phonology, morphology, syntax, semantics, pragmatics, discourse and so on. At every stage there are ambiguities. So, these ambiguity resolution happens either by rule based methods, which is the knowledge based classical approach to NLP, or it happens by machine learning based method, which is statistical in nature. Then we moved on to shallow parsing, where we discussed part of speech tagging. This required understanding a very important machine learning algorithm, hidden Markov model, and the associated algorithms. So, this was covered. In hidden Markov model, we covered Viterbi algorithm, forward backward algorithm, and the Baum-Welch algorithm, and their usage in estimating the sequences. Its main usage is in shallow parsing. We also delved in a bit into Indian language part of speech tagging, which is a very challenging and important issue, and its usage is supreme in the context of various machine learning, machine translation and cross-lingual search projects going on in the country. Then we explored a bit the information retrieval topic, and its relationship with natural language processing was addressed. Then we moved to a very important topic, namely the topic of words and disambiguation. Both unsupervised and supervised algorithms were covered. Knowledge based algorithms also were looked at, but we gave a lot of emphasis on the Lec algorithm. This is an overlap based algorithm, and its usage was explored in detail, followed by supervised and unsupervised and semi supervised methodologies. After finishing words and disambiguation, we started discussing parsing. Words and disambiguation occupied a major chunk of lectures, probably about 10 lectures. Then in parsing, we used about 5 to 6 lectures to cover deterministic algorithms, classical algorithms. Then we moved to probabilistic parsing. In probabilistic parsing, the inside outside algorithm, the inside probability, the CYK algorithm, and how it influences probabilistic parsing too were covered. So, in particular, I must say that I enjoyed teaching this course by covering both the knowledge based techniques in natural language processing and the machine learning probabilistic based methods. These two together form the core of natural language processing in modern times. We did not cover large applications like summarization, machine translation. We did a bit of machine translation in the course, but not a whole lot. Information extraction, these were not covered. These are for a subsequent advanced level course. I hope the techniques covered in this course will be useful to you in your future studies of language processing, which is a very exciting field of artificial intelligence. Thank you.